Okay, so this is lesson 2.1 on periodic trends. In class, I asked that you guys memorize this pattern. This box right here represents the periodic table. As you move to the left and down, the size of the atom gets larger. Another word for size of the atom is atomic radius. And then as you move to the right and up, the size, two things increase: the ionization energy and electronegativity, which we'll talk about later. All you have to do is memorize this for now. We're going to talk about atomic radius first, and then we're going to get into ionization energy, and lastly we're going to talk about electronegativity. But for now, just know that as you move to the left and down, the size of the atom gets larger, and as you move to the right and up, the electronegativity and ionization energy increases. So those are just patterns that we tend to see. Here's the first one. This represents the periodic table. As you look at this, you'll realize that as you move to the right and from the right to the left, the size of the atom increases, and then as you move down, it also increases. But my question here is why? Why do you think that's the case? So I want you to pause this and think about it. Why is it that as you increase the atomic number, the size is shrinking in this direction, but as you move down, it's actually getting larger? So what's going on? Why do you think this is happening based on what you already know? Go ahead and pause and then press play. Okay, in order to answer that question, we first have to recognize that when there are more orbitals around the nucleus, we call these electron clouds. The size of the atom actually gets larger. And we also have to consider that the more positive the nucleus is, the larger the attraction for the outer electrons. Okay, so we have to take that into consideration. Whenever the nucleus has a large positive charge, it has the power to take in these outer electrons, not take them directly in, but it pulls them towards itself. We call this ZEF. Okay, ZEF is called the effective nuclear charge. ZEF. Okay, the more positive the nucleus is, the larger the attraction between the outer electrons and the nucleus. ZEF also takes into consideration that electron-electron repulsion does occur. So yes, the more protons, the more electrons as well, and there are repulsions, meaning that the electrons repel each other, but at the same time, you got to consider that the positive charge is what matters more, and the larger the nucleus's positive charge, the more attraction, despite these repulsions that occur on the electron clouds. And also the nuclear charge is stronger than something called electron shielding, which we'll talk about in a bit. But to answer the question, why is it that atoms get larger as you move to the left, and why is it that they get larger moving down? The answer is found in this slide. As you move to the right, you add an extra proton. You add an extra electron. But because I just mentioned that the nuclear charge is very, very strong, the more protons there are, the more nuclear charge we have, and the more the nucleus will pull on those outer electrons. And if there's a lot of pulling, then the size will shrink. And that's what we see here. Despite the fact that we keep adding electrons, it's still getting smaller because the nuclear charge is what matters here. But if we move down, the proton number also increases. So why is it not shrinking? Well, going down, yes, there are more protons, but also we have to consider that we have a lot more orbits here, more layers of electrons, more orbitals. And because of that, the atom will get larger. Here, as we move left and right, we only are dealing with one orbit, one orbital really, or a few, but it's very similar. So when we're moving across a row, protons is what matters. It's what determines the size. As we move down a column, what matters is the amount of orbits that an atom has. The next thing we have to consider is something called Coulomb's law. So there's a lot of words here. You could just listen and I'll basically summarize this. But what you need to know is this formula right here. So the F stands for force. There's usually a little a right there. The way it works is that the atoms tend to, two atoms can attract one another, but also the nucleus of one atom can be attracted to the outer electrons because they're oppositely charged, right? So this formula helps us understand the magnitude of the force, the attractive force among two things. So for example, Q here represents charge. Q2 represents the charge of something else. It could be an atom, it could be an electron. And R represents the radius. Okay, sometimes you might see it as d squared, okay, or r squared. K just stands for a constant. Don't worry too much about it. Just constants allow us to change units. But basically, when you have a large charge here and a large charge there, the attraction is going to be stronger. Whenever you increase the numerator, you increase the answer, the numerical answer. However, if you increase the distance between two things, then this guy is going to decrease. So the further away the electrons are, the lower the attraction the nucleus is to those outer electrons. Or we could think of it this way: the more positive charge the atom is, the nucleus is, the stronger the attraction. Okay, so everything that I just said basically is right here. You might want to read through this, but you really need to understand this formula right here. Okay, we're gonna skip this slide. You can read it on your own, but I want to explain something called electron shielding. And I'm gonna go back to this slide. So this is lithium, sodium, potassium. This image is a little deceiving just because lithium is right here, sodium is right there, and potassium is right there. So we're actually looking at this from up and down, so from the column's perspective, not a row's perspective. So just keep that in mind for this image. So I want to explain what electron shielding is. So here is a positive charge. The nucleus is attracted to these 3 electrons. But then here in sodium we have even more electrons and more orbits. And the attraction between the nucleus and the outer electrons here is actually less. And that's why the atom gets larger, because there's less attraction. And here, even though there are more protons, there are a lot more electron orbits here. And so the attraction between the nucleus and the outer electrons is actually much smaller, despite the fact that there are more protons. The attraction is smaller because there's so many electrons here that are getting in the way. When there are a bunch of electrons getting in the way, we call this electron shielding. So electron shielding means that there's all these electrons repelling one another, they're vibrating in space, and because they're getting in the way, the attraction between the nucleus and these outer electrons diminishes, and so the atom gets larger. We could also think of this from Coulomb's perspective, where the larger the distance, right, the larger the distance, the smaller the force. So the larger the distance here, the smaller the attractive force, and the smaller the attractive force, the larger the atom gets. So hopefully you guys can make that connection. So that's what that explains. I also want you guys to memorize this. ZEF, which is nuclear attraction. Think of ZEF as nuclear attraction, okay? I would probably add that on there. Just think of it as nuclear attraction. So as you move to the right, ZEF increases because you guys know that there's more protons, and you guys know that the shielding is very similar, or it's the same because it's the same number of orbits or similar number of orbits. But as you move down, we can't take protons into consideration. We have to take orbitals into consideration. So the more orbitals there are, the more electron shielding, and the more electron shielding, the lower the attraction. So that's why ZEF decreases. It decreases moving down. So left and right, protons, up and down, think of electron shielding. Okay, so it's just a blown up version. And the last thing I want to go over here is this idea of charges. So lithium here has a size of 1.23 Armstrongs. And then when it has a positive charge, when it loses an electron, it actually gets smaller. The same happens with these guys. And then when it gains an electron, it gets a little bigger. So the question here is why? Well, why does lithium get smaller? If lithium loses an electron, that means that the nucleus is going to be more attracted to the electrons that are on the outside because there's one less electron that is shielding or getting in the way. So we're removing electrons, we're not removing any protons. The number of protons stays the same. So because we remove an electron, the nucleus is able to pull in those outer electrons a little bit more tightly, and that causes the atom to shrink dramatically. The same happens here. Because here there are more electrons, we are adding more to the electron shielding effect, and that causes the atoms to get larger. So the attractive force, ZEF, actually decreases in this situation. And then here are some examples. You could go over this example down here, and you guys could determine whether these trends, why the trends are the way they are, so you guys could figure this out. So go ahead and take a minute and see if this makes sense to you, okay? And see if that makes sense as well, based on what we learned, okay? And we go ahead and press the pause button and see if you could do this problem. So I want you guys to rank these three species. We could call them species from smallest to largest in terms of atomic radius. Okay, now that you tried, you guys probably started by looking at the periodic table, and you notice that sodium is way on top. So sodium is smaller than potassium, right? However, we're recognizing that Na plus and K plus are going to shrink dramatically. So that means K is probably going to be the largest. So K will be the largest. Because if these two shrunk, then this guy must be the largest. And also we know K is larger than sodium. So because both of these shrunk, we could look at them from the point of view of the periodic table. We know that sodium is smaller than potassium. So that means K plus is going to be a little larger, and then Na plus is going to be the smallest. So that should be your answer. Okay, so this is the first part of the podcast.